comparatively.
Okay. Welcome, everyone. Happy Tuesday. Thank you for joining us today on our webinar concerning the pulp and paper industry. My name is Elsa Cantu. I'm the Regional Marketing Specialist for North America, and I am here to introduce Pearly LaChance. He will be doing the presentation today on the webinar. He is our Senior Regional Engineer, and he is based in the Southeast region. Pearly has lots of experience in the reliability and maintenance area. He also has experience in the power and chemical industry. He has actually worked for John Crane for 11 years, and the last 2 years being the reliability engineer for the East region. Pearly has a degree in mechanical engineering from UNC Charlotte and is a US Navy veteran. Finally, Pearly has great hobbies like remodeling and woodworking. Fantastic, I was able to say that. So with that, I'm going to pass it over to Pearly and we can get started.
Thank you, Elsa. So I wanted to start by introducing that on our website, the John Crane website, there are case studies out there that are available for your use, and the roots of what we're going to talk about today is actually a case study that's out there already. That case study was done about 2 years after the first seal was installed in this application. So the information is a little dated at this point, and Elsa and I have agreed that we would go and update this because the initial installation of this seal was done in December of 2015. So this case study that's online is about 3 years old now. So I just wanted to introduce that so you guys know that there are some pretty good case studies out there if you're trying to sell a certain product or decide if a certain product would work in a certain process.
Hey, Pearly, can you put the presentation and presentation mode?
How's that? Can everyone see the presentation?
Let's see. I see it in, let's see, I'm going to put it back. Okay, I do not see it in presentation mode. So let's, yeah, it's not fixed yet. Just got a text.
So for those of you that are familiar with the pulp and paper industry, there's a lot of different chemicals that are used in the bleaching process. You can use chlorine gas, sodium hypochlorite, oxygen, hydrogen peroxide, ozone, or chlorine dioxide like we're talking about. The chlorine dioxide use has actually increased quite a bit because of restrictions on use of chlorine gas. And the use of chlorine dioxide is not necessarily a new chemical for this process. It actually started in Sweden like back in the 1950s and was introduced to the craft process in the 1960s, and it's been widely used since then. The problem with chlorine dioxide is it's highly toxic. The limits on it are 0.1 parts per million. It can be an irritant to the lungs, cause pulmonary issues, irritation to the eyes and skin. It's also highly flammable and reactive, and that's why the DOT forbids transporting this unless it's hydrated. It's not hydrated form. So typically what the plants do is they actually produce chlorine dioxide right there on the site and transfer it to the process. Because of its reactivity, the fixed equipment, it's tile lined or acid-proof bricks used on the towers. It's plastic line or ceramic type piping. And when you're talking about the rotating equipment, you're talking about using titanium, PTFE, and perfluoroelastomers. And typically you're talking about a double seal to make sure that you prevent release to the environment itself. And again, the materials of construction for that would be titanium and perfluoroelastomers. So the history was we actually had an on-site reliability engineer on this facility. And so we were doing failure analysis of the competitor seals as they were coming out. And one of the things they noted right off was that there was a O-ring chemical compatibility issue. And so they took actions for the John Crane seals that were going in. Again, they were a standard double seal to address O-ring issues. The other issue was there was reverse pressure conditions that were occurring. And so there was efforts to make the customer aware that we needed to address the reverse pressure conditions. But the problem is that mill water is actually used as a barrier fluid for this. And so whenever there's a huge demand on the mill water system itself for, say, doing washdowns, it was interesting because I was just at this plant last week doing an installation in a different area. And to clean up the paper stock that was on the equipment and the floor, they basically hook up a big hose to the mill water system and they just start washing everything down. So you can imagine what happens to the header pressure when you do this. And that was the causes of a lot of these reverse pressure conditions that they were seeing, is that there'd be huge demands on the system. The other thing is the quality of the water they choose for mill water isn't typically what we consider pure water that you're using or clean water that you're using for a barrier system. Excuse me. So the MTBR for this application was about 1.5 years, and even after taking actions to address the O-ring compatibility issues, trying to address the reverse pressure condition issues, it pretty much stayed at 1.5 years. So we had to come up with something new. So it was pretty simple what we needed to do as far as the seal itself. We needed to have a double seal that was pressurized, again, to prevent release to the environment. It needed to address anything that would be susceptible to reverse pressure conditions themselves. And we needed to also make sure that we took care of cleanliness of the water being used for the barrier system itself. So the technology that we went after was what we call dynamic lift. And any of you that are familiar with the gas seal technology, where you use spiral grooves and you inject nitrogen to the seal and it causes the faces to lift off, this is the same technology, except we're using it in a wet application. So as the water enters the ID of this ring, it runs along these spiral grooves, and when it gets to the end of the spiral groove, it creates a pressure spike at those points. And if you look at the graph to the side, you'll see as it comes through the groove, you maxes out pressure. And that pressure can be as high as 200 psi, and that's depending on seal size, speed of rotation, on what the max pressure it'll develop. And then as it goes across what we call the sealing dam, this area with no spiral grooves, you see that it slowly and linearly decreases to whatever the stuffing box pressure is. So the nice thing about this seal is, even though you can have a low pressure on this side that's less than barrier, or excuse me, process pressure on that side, it acts like a Plan 53 in that the pressure at the seal itself is higher than the seal chamber pressure. So in our case, where we have fluctuations of this pressure here, we only need 5 or 6 pounds of pressure on the tank itself. And actually the initial testing of these seals was done with basically just a static head of an open tank. So, you know, it might've been a couple feet of pressure. So you don't really need a lot of pressure to the seal for it to develop that using the spiral groove technology. And I mentioned the sealing dam. That's how the seal actually seals. When it's in a static condition, this area out here acts like a plain face seal, and it provides sealing during the standby conditions. Any questions on how the spiral groove, the dynamic lift works? So some of the drawbacks of the dynamic lift is, unlike a true contacting seal, which has parts per million of leakage across the inboard faces. In our case, because it's a non-contacting seal now, the sealing gap is actually larger. So you end up with a consumption of about 1 to 2 gallons per minute going into the process itself. So if the process is very sensitive to in leakage, the upstream pumper is probably not the right seal. But if you consider pulp and paper, where we're using double seals and we're pretty much dumping barrier fluid to the ground, they have high consumptions of water. Or if you're talking a single seal or packing, they have pretty high flush rates of probably 1 to 2 gallons per minute going into the process. So for the pulp and paper industry, this is an excellent technology in that, you could drastically reduce leakage into the process if you're going from a single seal or packing to an upstream pumper. The other thing is, because of those spiral grooves, the water that's used for the barrier system has to be very clean. Otherwise, you'll start clogging these spiral grooves. And if without the spiral grooves, obviously you don't have the pressure pulses, and therefore the seal will start acting as a contacting seal there. And that'll wear out the seal, and it'll end up with reverse pressure conditions occurring. The other thing is on our application, because the temperature of the process is pretty low, it's the ambient temperatures, we actually use what we consider a dry running carbon outboard, our 5610D. And we do that for one main reason, is that it creates very little heat. So if you have a non-contacting seal inboard and you have a dry running seal outboard, you'll generate very little heat in this seal, and you can run the barrier system as a dead-ended system. So you don't need it in and out to the seal. Because this is a dry running carbon, again, the barrier fluid needs to be fairly clean to prevent you from abrading that carbon.
Hey, Pearlie, it looks like you do have a question here.
Okay.
The question was, you stated consumption at 1 to 2 gallons per minute. Should it be 1 to 2 gallons per day?
What I said was, on a typical single seal or packing, consumption would be 1 to 2 gallons per minute. But for the upstream pumper, it would be 1 to 2 gallons per day.
Okay.
Thanks for making sure that was clear.
Yes.
So for the new double seal, like I said, it was installed in December of 2015 with the dynamic lift on the inboard. And this would address any of the reverse pressure conditions that we were seeing on the mill water. Because again, in our case, since there was a traditional double seal installed there before, there was a seal pot. And so we left that in line with the seal, so that if they ever do completely lose seal water to the seal for a temporary amount of time, we have about 2 gallons of water in that seal pot that can be used to provide sealing to this seal. So again, if it's only consuming 2 gallons per day and you get 2 gallons in the pot, theoretically you have a day's supply there. And typically they won't be doing washdowns for 48 hours. So there's significant water available to that. We also use the non-contacting seal faces for low heat generation. And that was the same reason we went with the dry running outboard, was to lower any heat generated by the seal. The seal pot arrangement, we ended up taking the mill water, which is at about 40 pounds pressure. We reduced the pressure down to 5 PSI going to the seal pot. We put a 5 micron filter in line with that makeup water downstream of the regulator, and that will ensure clean water to the seal. Again, because the consumption is so low, you're talking 1 to 2 gallons per day, theoretically, what, 700, a little over 700 gallons per year. That filter element will run for a long time. And what we've actually seen in some cases, because the consumption is so low, the thing that we're most worrisome about is actually algae growing in the the filter. So that's one thing that the customer will have to keep an eye on, is to make sure that they don't have some kind of biological growth occurring in their filters because of the stagnant conditions. So once the new technology runtime actually exceeded the old 1.5 MTBR, the decision was made to go ahead and convert the other transfer pumps over to the same technology. Because of the success, in October of 2018, they decided that they wanted to use the same technology on their high shear mixture seal. And last week when I was on site, access to the chlorine dioxide transfer pumps is not easily accessible because of the hazards over there. But I did go by the high shear mixture seal to take a look at it, and still performing well over there, no issues. And a matter of fact, the original chlorine dioxide transfer pump seals still running at this point. So we're talking close to 5 years of runtime. So we've gone from 1.5 year MTBR to a seal that could run at least 5 years at this point. So I'll open it up to any questions that you guys have on the this application. Again, to let you know, we will be updating the case study that's online in the near future to make sure all of this new information is captured in there. But again, for a very toxic, hazardous environment type seal, this technology has worked very well for us.
So Pearlie, I do have a question for you.
Yeah.
One of the questions we've got here is, what barrier fluids can be used with the upstream pumper?
So the initial design basis was on water. So there are limitations on the upstream pumper in that we prefer to use water, and at ambient temperatures, again, you can run this dead-ended. As you get to higher temperatures, up to, and the literature will say 250 degrees F, we need to run a seal pot. We run it as more of a traditional seal with cooling water to the pot with an in and out on the seal. It can be equipped with a pumping ring, but we are looking at other barrier fluids right now to actually run this on. We've done one recently that's using ethylene glycol, but it's for a chemical monomer system where they were running high temp metal bellows seals. The thing with that is the barrier fluid still has to perform like water as far as specific gravity and viscosity at its operating temperature. So in our case, the glycol will actually be maintained at 220 degrees F to ensure that we will get proper liftoff at the faces.
Gotcha.
But go ahead.
Okay, because we've got like 5 questions, so I want to make sure I get them all in time.
Okay.
So has this technology been used in a different fluid than water as a barrier if water is not compatible with the process?
Like I said, I don't know the status on the install yet. I know that the customer has bought the one for the ethylene glycol used in monomer service, but I'm not aware of any other applications right now that have actually been running in the field with anything but water.
Next question was, are the inner seal faces SC versus SC? Do you know what that means?
Yes.
Okay.
So it depends on the application itself. Typically, we run carbon as the primary ring, and silicon carbide has the spiral grooves in it. But if you get into higher pressure applications, certain chemical applications, we will definitely run silicon carbide versus silicon carbide inboard. That's evaluated when the process is evaluated as far as what kind of pressures we're going to need to maintain, and what kind of speeds we're going to be running, and then what is the chemical compatibility requirement. You can also use tungsten carbide, but it's not typical that we would do that.
Okay. Next question is, what is the max operating temperature?
Again, it's 250 degrees F, but we have actually done some at higher temperatures. They have to be evaluated, and we would have to provide cooling to the seal itself to ensure that, because you got to remember, again, we have water as a barrier fluid. If the temperature due to heat soak is too high, we'll actually flash the water prematurely, and we won't get the liftoff of the sill faces. So the brochure will say 250. Anything above that will need to be evaluated. That's 250 F.
Okay. So the next question is, what is the difference in the fabrication or materials to allow the lift seal to operate in a liquid environment?
So the it's really that it's more like, for any of you that know our gas seal lines, it's more like the 2874, where the on the inboard sill faces, where the process is actually on the ID of it that you're applying. Excuse me, the barrier fluid is actually on the ID of this seal ring, unlike the old 2800s where the spiral grooves were on the OD. So it really has to do with where the grooves are being applied, but the theory behind it is basically the same.
Okay. What is the lowest RPM that these can be applied to?
Again, what you'll see in the literature is 1500 RPM, but we have actually done studies and done applications that are as low as 400 RPM. Again, anything under 1500 will be evaluated by the upstream pumping design group.
Okay. I just have a couple more questions and I think we are done. So here's the next question. Any issues with the 1 to 2 GPD water injection into the CIO2?
No.
Okay. That was easy. No. Okay. Is there anything that prevents you from trialing with a hydrocarbon barrier fluid?
Again, as long as the properties of the fluid, it acts like water at operating temperatures.
Okay.
And again, the glycol example, that's a Plan 54. So we will actually bring that glycol temperature up to 220, because you got to remember that the monomer, you can't even pump it until you're above 300 F. And so everything will already be at, close to operating temperatures through jacketing of the piping, the pump, heating of the barrier fluid to make sure that the faces are not stuck together. So I would say that unless you can't get the barrier fluid to an operating temperature prior to starting, that would be the one thing that would prevent you from doing that.
Okay. Can you elaborate a little bit more on acts like water?
Yeah, that's basically the viscosity and the specific gravity of it are similar to those of water at the operating condition.
Okay. So it's 11:25, so we've got time for just a couple more questions here. Does the addition of the excluder change operating parameters?
No, it's
Okay.
still the 250 degrees, and that really goes back to the barrier fluid itself being considered water. And so unless you're operating at much higher temperatures that we're evaluating, then we might remove the excluder, because it's only good to about 300 degrees F, because it is a PTFE material.
Okay. And last question that I have for you at this time is, what are the factors that increase 1 to 2 GPD leakage into the process?
So the differential pressure across the spiral grooves will have a significant impact on that. So depending on what your stuffing box pressure is that we're going into, the amount of pressure developed by the spiral grooves, which will be dictated based on the size of seal and the speed at which it's turning. are probably the biggest factors. There are charts that we can reference, and we do have web calcs that we can run your application through to give you a better understanding of what the actual in leakage is going to be. We actually have some customers that run these both inboard and outboard, which means both of them are non-contacting, which means the outboard seal is dripping onto the ground, and their thought process is that they know that it's working properly if they can see it dripping a little bit. But that's in a mining type application.
Okay. So Pearlie, that are all the questions for today's call. Thank you very much for everybody attending. Just a couple of housekeeping items before you drop. We'll follow up with a recording of the session, so we'll send that to you. I do have all of the questions as well, so I would like to send them back to everyone with those particular answers. And again, thank you for your time today. And Pearlie, thanks again for hosting and presenting this paper. Much appreciated.
Thank you.
Y'all have a great day. Thank you.
Thanks.